All right, I've got Einstein in an elevator, and it's hard to recognize what's happening here if you don't sort of have a context for this, because I think that things have changed a little bit. You guys recognize that Einstein's standing on something, though, right?
Yeah.
So the something that he's standing on here is meant to be a scale, like you would find in a doctor's office. You know, the kind that has like the whole stand up top so the doctor can read your weight and all that sort of thing? So Einstein's standing on a scale, and I want to give this situation a little bit more detail. So let's give ourselves a reference frame. We'll make up be positive and down negative. Up and down. And we'll let that reference frame stand for the whole page, so we don't have to keep on drawing it over and over again. But in this situation, he's standing in a stationary elevator. And we'll give him a reasonable mass, like 80 kilograms. And assuming the elevator's on Earth, we'll say that it's 9.81 meters per second squared, and we can say that it's down. And if it's a stationary elevator, then Einstein has a velocity of 0 meters per second. And what's more, if it's a stationary elevator, the acceleration of the system should be 0 meters per second squared. And the sentence at the top of the page, the sort of header says, let's find the reading on Albert's scale as he rides an elevator. And if we're trying to find the reading on the scale, what force are we trying to find? Normal force. Yeah, we're looking for the normal force, because that's what scales read, is they measure the normal force. Just to differentiate this, let's make sure that we know that his actual weight is defined as force due to gravity, which we could calculate as mass times acceleration due to gravity. 80 kilograms times, what direction is gravity? Acceleration of gravity is down, so I'm going to throw in a negative sign right here for the direction of gravity. 9.81 meters per second squared. That's negative sign standing in for down in our math. And if I do this math, I end up getting 784.8 newtons to the negative. Another thing I might think about with Einstein, remember, we're not doing a free body diagram here for an elevator. We're doing a free body diagram for the person. And the person would have that Fg acting down on him, and he would have a normal force acting up on him. So just to be clear, this is the person's FBD, free body diagram. And every time we do a free body diagram, we can set it equal to F net. And I don't know how many times I thought it, and I don't know how many times I've said it, but you never, ever attach F net to the free body diagram. F net is equal to the free body diagram. It's not one of the forces on the free body diagram, okay? It's the sum. And we also know that F net not only is equal to the sum of the free body diagram, but it's equal to Newton's second law. F net is equal to the mass times the acceleration of the system. In this case, the system's just a person. So then I say, okay, well, I can make up that equation. I can say F net is equal to F normal plus Fg. Remember, I'm trying to get F normal. So I'll get F normal all by itself. F normal is equal to F net minus Fg. F net's equal to 0, isn't it? Look at this. How do I know that F net's equal to 0? Yeah. Yeah, look, if F net is mass times the acceleration of the system, and the acceleration of the system is 0 meters per second squared, yeah, it's 0. So I can zero that guy out right away. And so I can say, okay, well, F normal then is going to be equal to negative Fg, so negative of negative 784.8 newtons. And at least for now, I'm still emphasizing that one of those negatives was from algebra and one of them was from the reference frame. And so that means that it's 784.8 newtons. And I can say that it's up. or I can round it off to significant figures. Looks like I had 3 significant figures, so approximately 784 newtons up. And we could write a little therefore statement or something like that, and that's fine. But what's that? Oh my goodness, you're right. How did I? It's the morning. I should have a coffee. That should be a 5. Thanks for catching that. Yeah, not enough bananas in the morning. All right. All right. Now, I want to put this out there that since it's Einstein, I'm going to use an Einstein word. Einstein calls a situation that's not an environment that's not accelerating, he calls that an inertial reference frame. That's a new word, an inertial reference frame. An inertial reference frame is an environment, a reference frame that you find yourself in that isn't accelerating. Okay, so maybe I'll make a little note to myself about that, just to remind myself. This is a situation where the velocity of the environment is constant. In this case, the environment that he's in is his elevator. Acceleration is 0. That's interesting. When he's in an inertial reference frame, there's a name for that. I want to come back to this later, though, okay? Let's take a look at another ride. Later on, Einstein finds himself in an accelerating elevator. And even as I write this, is this inertial or non-inertial? Inertial. If it's an accelerating elevator, will it be inertial or non-inertial? Non-inertial. If inertial is constant velocity and the elevator is now accelerating, it's not inertial anymore. But we'll see if there's a consequence for that. Anyway, it's the same person, so they're still 80 kilograms. They're still on Earth, still 9.81 meters per second squared down for acceleration to gravity. But we said this was an accelerating elevator. So I can't say that the velocity is 0. I'm just going to leave that one blank. But I'll say the acceleration of the system now is 5.00 meters per second squared. And I want to say that this one is accelerating upwards. Okay, accelerating up. I just have an up arrow there. Accelerating up. Now I can borrow some information from the previous run through and I can say, well, it's still the same fella. So I can say, well, force due to gravity acting on this person is still going to be 784.8 newtons. I'm just borrowing that from my earlier thinking. New thinking this time is I might be thinking about F net. F net for the system is going to be equal to the mass of Einstein times the acceleration of his system. And I can get the acceleration, oh sorry, I wanted to get F net, what am I saying? The F net for the system, I can just plug in my values, 80 kilograms times, hey, is this 5 going to be a positive 5 or a negative 5? Positive. You sure? Say I'm positive. All right, 5 meters per second squared. 80 times 5, anybody do that in their head? 400, yeah. I mean, I could say that it's positive 400, but it's 400, yeah. 400 newtons. And then I fall back on my free body diagram. You know, the beauty thing about this is that the free body diagram hasn't even changed. It's still the floor pushing up on him and gravity pulling down on him. And that's still equal to F net. You know, I guess I specified that it was F net for the system, and now I'm just calling it F net. Same thing, okay? Because it's just one object. I say, okay, well, I can come up with an equation for that. We did it once before. We say F net is equal to F normal plus Fg. And once before, because we've already done this, we can say that F normal.
Attention, Nelson. At this time, all CPP students are supposed to be making their way
F
down
net
to
minus
the large
FG.
gym. Again, all CPP students, please make your way down to the large gym. Thank you.
And we can sub in our values. We got an F net value. We found out that it was 400 newtons. Minus FG. Remember that FG is a negative value. So it's minus negative 784.8 newtons. Somebody who's quick on the calculator, what do you get? What you got? Nice. Beautiful. 1,184.8 newtons. And as I look at that, I think, hey, does this make sense? The floor is pushing up on Einstein harder when the elevator accelerates than when he was just sitting there. Yeah, I think that makes some physical sense. We can talk about that as people who have ridden elevators. And the thing that we said earlier was this would be a non-inertial reference frame. Now, the only reason I really bring this up is because later on, maybe at a later grade, we'll talk about inertial and non-inertial reference frames as it relates to special relativity. We're not there right now. But one of the postulates in special relativity is that as long as you're in an inertial reference frame, everything's going to behave just like you'd expect. Everything is going to continue on as if you're sitting still. But when you're in a non-inertial reference frame, things change. And in this case, when you're in a non-inertial reference frame, the thing that changes would be that you would feel a normal force that's not going to be equal to gravity. That makes sense. Now, we could talk about other things. Like, for example, if I throw a ball up and down when I'm in an elevator that's stationary, it would appear to behave differently than if I throw a ball up and down while the room itself is accelerating upwards. Can you imagine that the floor would accelerate up to meet the ball? Like, there would be multiple things that would be funny about being in an accelerating elevator. In fact, if you continued accelerating forever, blasting off as a rocket ship, things would be kind of weird, right? Like, I mean, the blood would pool in your feet, all that sort of stuff. It wouldn't be as if you're sitting at constant velocity. Anyway, just quick little note, the velocity is changing. The environment is accelerating. Okay, so I'm just throwing that out there as a word that we're encountering. And it is related to Einstein. Sort of a precursor talk about special relativity, I guess. All right, so, what's that? Oh, rounded to sig figs, you're right. What should that go to? 3 sig. Ooh, I guess we should be at 1180. 1,180 newtons. Okay. Okay. All right, let's take a look at another situation. So here's Einstein moving at a constant velocity. Constant velocity elevator. And you know, this could actually be a story. You know, you get into the elevator, it's sitting still. Then the elevator motor kicks in and it starts to accelerate. Elevator gets up to speed and it coasts along at a constant speed until you get to your floor. You know, and I've been in elevators like this. If you ever been in the elevator at the CN Tower or Empire State Building or one of these, and I've ridden both of those elevators. You know, it's like one of those things, you know, you got to do it. But I felt this. I got into an elevator and I felt normal. The acceleration increased and I felt a little heavier. Well, let's talk about what's going to happen once it gets up to speed, okay? So that's all. Same person, mass is equal to 80 kilograms. Still on Earth. You know, could be at the CN Tower, could be at Empire State Building, depending on where you are along the border, North America, 9.81 meters per second squared. Let's just say that this is a great elevator that gets up to 7.00 meters per second. That is quite the elevator. You say, ooh la la, ooh la la. That's a nice elevator. And it's going to go up. So I think I'm just going to say, well, if it's up, it's going to be positive. Let's write it a little bit differently this time in our givens. Now, if it's going at a constant velocity, what's the acceleration of this elevator? 0. Constant velocity means 0 acceleration, 0 meters per second squared. Hold on. We're still on Earth. So it's still 784.8 newtons due to gravity. Oh, you're right. I didn't give a negative sign to the acceleration due to gravity. But that's where that negative sign is going to be from the FG. And we're just carrying forward that same information because it's still the same fella. Now, when it comes to the F net on this system is equal to the mass of the system times the acceleration of the system. What's the acceleration of the system? 0. Look, this is the acceleration of the system. So if the acceleration is 0, if this term is 0, then the whole thing is 0. 0 times anything is 0. And the reason I bring that up is because we're going to have a free body diagram, just like we've had before, where there's a normal force on Einstein, there's a force due to gravity on Einstein equal to the F net. Generates an equation for us. F net is equal to F normal plus Fg. I get F normal all by itself. This is, see how when you do your homework, it gets repetitive, and you're just like, okay. And believe it or not, doing all your homework makes you not only better at writing evaluations, but faster, because it kind of almost goes on autopilot once you figure out what the patterns are. F net, not that you want to just operate on autopilot, but it helps sometimes if there can be a little bit of muscle memory. You know, like people go to the gym or people play tennis, badminton people, you get this muscle memory, like that flip of the wrist when you're playing table tennis. It just comes naturally if you play enough of it. You put a little spin on that ball. I love it. F net was 0, wasn't it? Shucks. All right. Minus Fg, which is minus that negative 784.8 newtons. And I'm almost feeling like a little bit of physics deja vu here because I'm going to get positive 784.8 newtons, rounded off to 785 newtons, up. And again, what Einstein says about being in an inertial reference frame is that whether your constant velocity is a 0 constant velocity or a non-zero constant velocity, the scenario feels the same. It feels like the same thing. And there's even a thought experiment out there. Einstein's famous for thought experiments. If you blacked out all the windows on a train and it traveled at a constant velocity and it had perfect shocks, because remember, if it bounces, it's actually accelerating up and down, perfect shocks. Could you even tell if the train was moving or not? Is there an experiment you could do to see if the train is moving or not? Oh yeah, I guess hearing it. If it was in a soundproof train, if you could block out all the external stimulus and just be in that train, if you're moving at a constant velocity, if that train's truly an inertial reference frame, you couldn't. You couldn't tell if you're stationary or moving. All those other things like bouncing or vibrations, they actually are slight accelerations to your system. But if it's a true non-inertial train, you couldn't tell whether you were stopped or if you're moving at a constant velocity. Sure, if you were on a train, if you were on a plane, if you were with a fox, or if you were in a box, if they were non-inertial, you would feel it. If it was inertial, you wouldn't feel it. All right, so this one again is an inertial reference frame. I would not, could not, in a box. I don't know, whatever you're doing with that fox. Eating eggs and ham, I think. All right, so if it's an inertial reference frame again, I'll put feels the same as if sitting still. That's interesting. All right. Let's pan back up to the top here. Einstein again. And if this is a single shot trip, we get in the elevator, engines kick in, coast at a constant velocity. Of course, you're going to get to your desired floor, and you will slow to a stop, right? And if you slow to a stop, then it makes sense that we could call this an accelerating elevator. But we could say that it's accelerating downward. And when I say that something's accelerating downward, that doesn't mean that its velocity is downward. It means that it could be traveling upwards and slowing down, right? That could be a negative acceleration. And we've dealt with that with projectile motion. But we have the mass of this person Not changing. Still on Earth. (9.81) still going to be negative because it's still gravity. I can't say anything about the velocity because it's slowing down. It's not a consistent velocity. I can say the acceleration of the system is going to be, remember, we're going to have negative acceleration this time. I think just to keep common numbers and make things easy on ourselves, let's say that it's negative, but let's say it's the same engine. It's able to accelerate positively at 5 meters per second squared, and it's also able to slow down at 5 meters per second squared, but negatively, okay? Let's pretend that that's how elevator motors work. And so we can carry the oh, not that one's not gonna carry forward. We can carry his force due to gravity forward because it's the same fella. So Fg is going to be negative 784.8. F net is not going to be 0 this time because it's going to be mass times the acceleration of the system. So it's going to be 80 kilograms times that negative 5.00 meters per second squared. Maybe some sort of acceleration due to braking or slowing down of the motor, however elevators work. And I only chose that so we could have some common numbers. So 80 times negative 5 is going to be negative 400 newtons. And moving on to the free body diagram for this slowing down elevator, we'd have a normal force, an Fg. And you know, as we work through this, you guys tell me, is the normal force going to be a bigger value than force due to gravity or a lesser value than the force due to gravity? Think it out. Tell the person next to you. Is normal going to be less than the force due to gravity, more than the force due to gravity, or the same as the force due to gravity? What's it going to be? Well, we'll see. So F net still equals F normal plus Fg. F normal still equals F net minus Fg. Remember, we already calculated F net and Fg, so we can throw that in there. Negative 400 newtons minus negative 784.8 newtons. Somebody help me out with the math. Negative 400 plus 784.8.
380.
Nice, 384.8 newtons. And we can round that off to 3 sig figs, 385 newtons about. Oops, 385 newtons. And we can say that that's up. And look at this. When I'm sitting still or in an inertial reference frame that's moving, same. When I'm accelerating upwards, the floor presses into my feet, increases the apparent weight. When I'm slowing down, it decreases the apparent weight, decreasing the normal force, as predicted. And we can throw this again. We can say that it's non-inertial. And we know that being non-inertial means that we have an accelerating reference frame, but it also means that the normal force isn't going to be what it would expect it to be if you were sitting still, right? And we should be able to make sense of this. Now, sometimes people will throw a curveball in this and say, what would you have to do for the normal force to be exactly equal to 0? Can you imagine? Let's take a look at that kind of extreme. You have some margins. You have some margins on your page, but I want to just pull out a Post-it note. You can do this in the top margin of your page. I want to think about, what if I wanted the F normal to equal 0? How could I cook this thing? Well, the formula wouldn't change. I would say F net, because the formula hasn't changed for any of these. F net would be equal to F normal plus Fg. But if I want the normal force to be 0, okay, that's fine. Then that means that the F net is going to be equal to Fg. In other words, the mass of the system is going to be equal to the mass times acceleration to gravity. Notice the masses cancel out. If the normal force on somebody's feet is 0, what's happening with this elevator? Yeah, isn't it? Look at this. Leo says it's falling. Can you see what he's saying? Somebody cut the cable. This is not a safe elevator. So the normal force shouldn't be 0. Well, I mean, hopefully it's not 0. What if you get a normal force that's negative? Let's think about what that would mean. I want to play a quick game on this one. Let's see. F normal. Let's just say that the normal force was negative 20. Negative normal force. What the heck does that mean? Well, the F net is still equal to F normal plus Fg. And based on our calculations, at least for this fellow, Fg was negative 784.8. So let's just see what that means. So negative 20 newtons plus 784.8 newtons. Is that how that worked out? Minus negative? No, that's not right, is it?
Plus negative.
Oh, yeah, it's plus negative. Yeah, 784.8 newtons. That's I don't know, looks like 804, yeah. Negative 804 newtons. I guess 804.8 newtons. And I think to myself, what is that? What does that even mean? Well, F net's equal to mass times the acceleration of the system. What we're saying here is that the acceleration of the system, F net over m, is equal to negative 804.8 newtons divided by 80 kilograms. What's 804.8 divided by 80? Somebody with a calculator. What's 804.8 divided by 80? What is it?
I don't know, I'm guessing.
You're guessing? Don't guess. No. 10.06? Okay. So the acceleration of this system is going to be 10.06 meters per second squared, but it's a negative value, right? So down. What is this elevator doing? Yeah, what is it? Yeah, it's accelerating downwards, but accelerating downwards at a rate greater than what? Yeah, this is an elevator that's falling faster than gravity.
You're getting sucked into something.
This is like some sort of a, I don't know, maybe somebody put a rocket on the ceiling of your elevator. Where are you standing in this elevator? Are you standing on the floor if the normal force is negative? Aren't you standing on the ceiling of a downward accelerating elevator at this point?
Yeah.
You should not be getting negative normal forces unless there's a good reason, right? So this would have to be something that we would need to know more about. I need to know why this elevator is doing this. Could this be an amusement park ride? Maybe. Sounds terrifying. Downward thrusting elevators that you stand upside down in. Oh my gosh, right? But if you ever get a negative normal force, ask questions about that. That's something that you really should be concerned about, okay? So I'm just throwing that out there. The negative normal forces have the possibility of excitement and danger. But they're probably wrong. I'm just saying.